Hello everyone, today I'm presenting Know What You Don't Know, Uncertainty Calibration of Process Reward Models. Research from MIT at NeurIPS 2025. In short, this work is about reliable and cost-effective LLM test time scaling. We do this by calibrating a process reward model or PRM so we can reliably estimate when an LLM is going to be correct. We then use this signal to build efficient, adaptive test time scaling. The result, we can save up to 70% of test time compute on mathematical reasoning tasks while maintaining their original accuracy. Let me show you how. Recently, a line of work has shown we can improve LLM's reasoning by scaling test time compute. The core idea is to generate multiple reasoning trajectories and aggregate them to get better answers.
Okay, class, who knows the answer to this?
But here's the question. Is using more test time compute always necessary? Imagine 10 students collaborating on every test question. Not just complex calculus, but also simple addition like 1 plus 1. This is obviously inefficient. And yet, this is exactly how current test time scaling works. It applies the same computes to every problem, regardless of difficulty, which can be a huge waste of compute. You might ask, can we use PRMs to estimate confidence and adapt compute accordingly? Unfortunately, we found this doesn't work. Here's why. The core issue is miscalibration. PRMs are trained using large models along with expert annotations. But at inference, we often use smaller models. This creates a mismatch. The PRM overestimates what weak models can do. Our first solution is to apply quantile regression for calibration. The core idea is to tailor the PRM to each specific policy LLM. We essentially fine-tune the PRM with weighted quantile loss, but we do it using calibration data generated from the target LLM. As part of this fine-tuning, we also change its output. Instead of one overconfidence score like 0.95, the PRM now learns to output a calibrated range of scores, like a 10% at 0.6 and a 90% at 0.8. So we get two key benefits. First, the PRM is now calibrated for the specific model we are using. Secondly, it explicitly quantifies its own uncertainty through this range. Our second solution, Instance Adaptive Scaling or IAS, uses this new calibrated reward signal, P, to determine the optimal test time compute in IAS. Let's return to our student analogy. For an easy problem like 1 plus 1, our calibrated PRM now reports high confidence. IAS sees this and makes a quick decision using minimal compute. So there's no waste. But for a hard problem like a complex integral, the PRM will report low confidence. This triggers IAS to allocate more compute, generating multiple reasoning paths to find the correct answer. So now we have smart adaptive scaling we wanted. What are the final results? Our IAS method achieves comparable accuracy to the fixed budget baselines while saving up to 70% of the compute. In other words, IAS could operate at just 30% of the original computational cost while maintaining performance. This directly solves the inefficiency problem we targeted from the start. In summary, by first calibrating PRM and then using it to adapt compute, we've shown that test time scaling can be both highly effective and highly efficient. This opens up new possibilities for deploying powerful reasoning systems at scale. For all the details, please check out our archive paper, GitHub code, and Hugging Face dataset, please. Feel free to reach out with any questions, and thank you for listening.